Tesla is named after Nikola Tesla, the man who invented the induction motor. So you'd think of all the EV makers on the planet, Tesla would be the one building every single car around that exact technology. It doesn't. And the real story is stranger than that. Tesla is the only one of these three companies still running two completely different motor technologies inside the same car at the same time, for a very specific engineering reason. Porsche and BYD each committed fully to one side of this argument. Tesla refused to pick. By the end of this video, you'll know exactly why, and which one of these two motor types is actually powering the car you'd cross-shop, even if the spec sheet never tells you directly. So first, the actual physics, because this is where the whole video hinges. Every electric motor spins because a magnetic field in the stationary outer housing, the stator, drags a rotating inner shaft, the rotor, around behind it. How that rotor gets its own magnetic field is the entire difference between these two technologies. A permanent magnet motor is the more intuitive version. The rotor has actual magnets embedded in it, usually built from rare earth materials like neodymium. Those magnets create a fixed, constant magnetic field that locks in step with the stator's rotating field, almost like a dance partner following a lead without ever needing to be told the steps. Because that magnetic field never has to be generated on the fly, permanent magnet motors deliver very high torque instantly and run extremely efficiently across most driving conditions. That's the upside. The downside is the magnets themselves. Rare earth mining and refining is expensive, geopolitically concentrated, and even when the motor is switched off, those magnets still create drag against the stator. A bit like leaving a bike with the dynamo light rubbing the tire the entire time you ride, whether you need the light on or not. An induction motor solves this completely differently. There are no magnets in the rotor at all. Instead, the stator's rotating field induces an electrical current directly into the rotor. This is literally Faraday's law of induction, the same principle Tesla is named for. And that induced current creates its own temporary magnetic field, which is what actually spins the rotor. No rare earth magnets, no expensive materials, and critically, no drag when the motor isn't being asked to work because there's no permanent field to fight against. The trade-off is that inducing that current constantly takes some extra energy, so at very steady, everyday loads, induction motors run slightly less efficiently than permanent magnet ones. And that efficiency gap is exactly what shows up on your range number over a long enough drive. There's one more piece worth knowing before we get to the three companies. Permanent magnet motors are also more vulnerable to a failure mode induction motors simply don't have: demagnetisation. Push a permanent magnet motor into extreme, sustained heat, repeated hard track laps with poor cooling, for example. And those rare earth magnets can permanently lose some of their magnetic strength, which means permanently losing some of the motor's power output. An induction motor has no magnets to damage in the first place, so it has no equivalent failure mode. The worst that tends to happen is the windings themselves overheating, which is a more conventional and more manageable problem. That single trade-off, instant, magnet-driven efficiency and higher demagnetization risk versus zero-drag flexibility with a simpler failure mode, is the entire reason these three companies ended up building three different answers. Porsche went all in on permanent magnet. Both motors in the Taycan, front and rear, are permanent magnet synchronous units. And once you understand what Porsche actually needed this car to do, that choice makes complete sense. The Taycan is built to survive repeated back-to-back full-power launches on a track without the performance falling off a cliff. Porsche has specifically engineered it to handle multiple consecutive launch control runs, something most EVs can't do without serious power derating after just one or two attempts. Permanent magnet motors give you that sustained, repeatable torque density without the motor needing to work harder just to maintain its own magnetic field, which also means less waste heat building up run after run. For a company whose entire brand is built on doing the same hard thing over and over without degrading, that's not a small detail. It's the whole point. Quick one before we get to BYD. If you've driven a Taycan or a Model S back-to-back, drop a comment on which one actually felt more consistent lap after lap. I want to see how this splits. BYD also went all in on permanent magnet, but BYD's reason for choosing it is almost the mirror image of Porsche's, and it says a lot about how differently these two companies are positioned. Porsche chose permanent magnet despite the rare earth cost, because performance mattered more than the sourcing headache. BYD chose permanent magnet partly because of the rare earth cost. China controls the overwhelming majority of the world's rare earth refining capacity, and BYD, as a Chinese manufacturer with deep vertical integration into its own battery and component supply chain, doesn't face the same material sourcing risk that Western manufacturers do. For BYD, the expensive, hard-to-source magnets problem that makes Western engineers hesitate barely exists. That's not a footnote. It's a genuine structural advantage baked into where the company is built, not just what it builds. Which brings us to the company that wouldn't commit to either side. And here's where it actually gets interesting, because Tesla didn't always build cars this way. The earliest Tesla Model S, launched back in 2012, used a single induction motor on the rear axle and nothing else. No permanent magnets anywhere in the drivetrain, full stop. It was a pure homage to the company's namesake, and it worked, but it also left efficiency on the table in ordinary daily driving. As Tesla expanded into dual-motor, all-wheel drive variants, the engineering priorities shifted, and the drivetrain architecture shifted with them. That's the version most people are actually driving today. Tesla's higher-performance dual-motor vehicles have paired an induction motor on the front axle with a permanent magnet motor on the rear axle, not as a compromise, but as a deliberate use of each motor's specific strength. In a rear-biased all-wheel drive Tesla, that front motor is barely doing anything most of the time. It only kicks in under hard acceleration or when the rear wheels lose traction. A permanent magnet motor sitting idle on that front axle would still be creating drag the whole time, quietly costing you range for a job it does maybe 5% of your driving. An induction motor sitting idle costs you nothing because there's no magnetic field to fight when it isn't being asked to spin. So Tesla put the efficient, always-on permanent magnet motor where the power is needed constantly, the rear, and the free-spinning induction motor where it's only needed occasionally, the front. It's a genuinely elegant piece of engineering, and it's also not the whole story anymore. Tesla has been actively working to reduce, and in some newer drive units eliminate, rare earth materials altogether. The same underlying pressure that shapes BYD's supply chain advantage is pushing Tesla to try to engineer its way out of needing those materials at all, rather than simply securing access to them the way BYD already can. And there's actually a fourth camp starting to emerge that's worth knowing about, even though none of these three companies are fully there yet. It's called an axial flux motor, and instead of the rotor spinning inside the stator like a rod through a tube, which is how every motor we've talked about so far is built, the rotor and stator sit face to face, like two dinner plates stacked with a small gap between them. That geometry lets the whole motor become dramatically shorter and lighter for the same power output, because you're not wasting space on a long cylindrical housing. Mercedes has already put an axial flux motor into limited production through its YASA subsidiary, and it's the kind of technology that could eventually make the induction versus permanent magnet debate we just walked through feel like old news. For now, though, it's a niche, expensive approach, which is exactly why Porsche, BYD, and Tesla are all still fighting this same battle over which conventional motor to build around. So what does any of this actually mean if you're the one behind the wheel? 4 things show up in the real world. Performance consistency. Permanent magnet-heavy setups like the Taycans tend to hold their power output more consistently across repeated hard runs, which matters if you're taking a car to a track and not just to a stoplight. Efficiency in mixed driving. Tesla's induction plus magnet blend is specifically optimized for the reality that most all-wheel drive driving is mostly rear-wheel driving, with the front motor waking up occasionally rather than working constantly. Long-term material exposure. BYD's vertical integration into its own supply chain is a genuine structural advantage that Western manufacturers, including Tesla, are still actively trying to design around rather than match directly. And repair cost, because permanent magnet motors are more failure-prone under extreme heat and rely on materials with volatile pricing. Replacement units for magnet-based motors have historically carried a higher parts cost than induction units doing an equivalent job. Something that rarely shows up in a first-owner review, but matters a great deal by the time a car changes hands. So next time you see dual motor or all-wheel drive on an EV spec sheet, you now know the question that actually matters. Are both motors the same technology, or is the car deliberately running two different ones for two different jobs? Porsche and BYD picked one side and built their entire drivetrain around it. Tesla is still, quite literally, running both. If this is the kind of breakdown you want more of, this channel exists specifically to take the marketing language apart and show you the actual hardware underneath it. Hit subscribe so the next one lands in your feed. Drop a like if this changed how you'll read a motor spec sheet from now on, and tell me in the comments, does Tesla's mixed approach sound smarter to you, or does committing fully to one motor type, like Porsche and BYD did, sound like the more honest engineering choice?